Welcome to the deep dive. Today, we're exploring the really ingenious ways military aircraft try to become less visible, harder for the enemy to detect.
Yeah, it's fascinating stuff. We'll be looking at manipulating electromagnetic signals, that's electronic warfare, and also how the actual physical shape and materials of the plane play a huge role.
Right. We got some great source material for you. Excerpts from Electronic Warfare DRDO on the signal side.
And stealth aircraft design, which talks about low observability, basically. The design tricks to make planes harder to see, especially by radar.
So our mission here is to pull out the most intriguing ideas, the key concepts behind this high-stakes aerial hide-and-seek.
We want you to get a good sense of how these technologies work and, frankly, why they're so critical now.
Okay, let's jump in. Maybe start with a real-world example, something that shows the impact of this stuff.
A perfect place to start is the Bekaa Valley, Lebanon, back in 1982. It's a classic early demonstration of just how decisive electronic warfare, or EW, could be.
Ah, yes, the Bekaa Valley. I remember reading about that. It really shifted thinking, didn't it?
Absolutely. It showed EW wasn't just defensive anymore. It was a primary offensive tool.
So how did it work there? The sources mention Israel using some smart deception tactics.
They did. They sent in drones, RPVs, remote piloted vehicles basically as bait. Their job was to get the Syrian SAM-6 missile radars to turn on to reveal their frequencies.
Like flushing birds out of cover, but electronically.
Exactly. A clever bit of scouting in the electromagnetic spectrum.
And once they had those frequencies,
Then, Israeli E-2C Hawkeye aircraft, these specialized command and control planes, used that data to pinpoint the exact locations of all those Syrian radars.
creating an electronic map of the danger zones.
Precisely. They knew where the threats were, and then came the attack.
They hit the missile sites with rockets, guided somehow.
Guided by microwave beams right onto the radar emitters themselves, turning the Syrians' own radar signals into beacons for destruction.
Wow. Talk about using the enemy's strength against them.
The result was, well, decisive. A major Israeli victory, largely credited to their mastery of electronic warfare in that battle. It really put EW on the map.
Okay, so that sets the scene. Now let's get into the fundamentals of EW based on our DRDO source. It breaks it down into ESM, ECM, and ECCM. Can you unpack those a bit?
Sure, think of them as layers. ESM electronic support measures is the passive part. It's all about listening, detecting, identifying enemy signals. Intelligence gathering, basically.
So ESM is the ears of electronic warfare, finding out who's talking electronically and where.
Exactly. And that intel informs everything else. What countermeasures to use, what targets to prioritize.
Okay, then what's ECM?
ECM electronic countermeasures is the active part. This is where you do something about those enemy signals. You jam them, you deceive them, you disrupt them.
Right, throwing static or false information into their systems.
Precisely. And then there's ECCM.
Electronic countermeasures.
Hmm?
So countering the countermeasures.
You got it. ECCM is about protecting your own signals from the enemy's ECM, making your radar harder to jam, your communications secure. It can be active, like changing frequencies rapidly, or passive, like building better filters into your receivers.
Okay, listening, acting, and protecting. Makes sense. The source also distinguishes between radar EW and communications EW. They're not quite the same game, are they?
Not quite, though the ESM, ECM, ECCM framework applies to both. But radars and radios work differently, so the techniques differ. For instance, radar usually has the transmitter and receiver together.
Like shouting and listening from the same spot.
Right. Communications usually involves separate transmitters and receiver locations, people talking across a distance.
And the signals themselves are different.
Yeah. Radar is usually two-way signal out, echo back. Comms are often one way, and encryption is huge in comms, but usually absent in basic radar signals.
So misleading techniques would differ too.
Definitely. For radar, you might create false targets, phantom aircraft on their screen. For comms, you might inject false messages or just disrupt the network. Different targets, different tricks.
Got it. Let's dig into some of the hardware, the subsystems our source mentions. First up, search and bearing equipment. What's that doing?
This is core ESM kit. Think of it as a sophisticated scanner, constantly sweeping the airwaves for signals. When it finds one, it tells the operator the frequency, the type of signal, radar, pulse, comms, etc., the direction it's coming from, the bearing.
And even the antenna rotation, if it's a radar.
Yeah, that helps identify the radar type and what it might be doing. It builds that real-time electronic picture.
Okay, then signal analysis equipment, taking
What?
that raw data and making sense of it.
Exactly. This gear measures the fine details. Pulse rate, pulse width, patterns, even harmonic content. Those unintentional extra frequencies systems sometimes leak.
Like an electronic fingerprint.
Precisely. It helps nail down exactly what kind of system you're dealing with and assess the threat level.
And this radio data transmission equipment, what's its role?
That takes the analyzed signal data, turns it digital, and transmits it securely to other units or command centers. It's about sharing that vital EW intelligence quickly.
So gather, analyze, share. Then comes the jamming transmission equipment. This is ECM territory, right? The active interference?
Correct. This is the gear that generates powerful microwave signals to mess with enemy systems. It can create broadband noise like electronic static to overwhelm frequencies.
Drowning them out.
Or focused spot jamming against a specific frequency. Or even deception jamming, sending back false echoes to confuse their radar about target location or speed. Power levels mentioned range from 20 to 400 watts, covering the frequencies the search gear is listening to.
Like shouting louder or mimicking their voice to confuse things. What about video blanking equipment?
That's about managing your own signals. In a busy electronic environment, your friendly radars or jammers can clutter up your own EW displays. Video blanking helps filter that out, so operators see the real enemy threats clearly.
Cleaning up your own screen. Makes sense. Now, radar itself. Radio detection and ranging. Still fundamental.
Absolutely indispensable. Works day, night, any weather. The basics as the source lays out. Transmitter sends energy, directional antenna focuses it, receiver picks up echoes, display shows the results.
And distance comes from the echo delay time. Simple physics.
Simple principle, complex engineering. The source mentions the duplexer, which lets the same antenna transmit and receive almost simultaneously. Very clever.
And there's a whole spectrum of radar frequencies, right?
Huh.
From VHF, UHF for long-range warning up to higher bands like X or Q for targeting.
Yeah, a wide range. Lower frequencies generally give longer range but less detail. Higher frequencies give more detail for things like fire control or mapping, but usually have shorter ranges.
And each radar has a unique signature.
Like that fingerprint we mentioned. Based on its power, frequency, pulse patterns, antenna stand, ESM systems learn these signatures to identify threats.
And radar silence. Just turning it off.
Exactly. MMCON emission control. Sometimes the best way to stay hidden is not to transmit at all. Just listen.
Okay. The source also mentions phased array antennas being important for ECM. What's special about them?
Their big advantage is speed and flexibility. They can steer the jamming beam electronically almost instantly without physically moving the antenna.
So you can quickly zap multiple threats.
Precisely. You can focus narrow beams of jamming energy very accurately, making the jamming more effective. They're used for self-protection on planes and for dedicated standoff jamming aircraft. Also great for quickly pinpointing enemy emitters for ESM.
And these lens-fed multiple beam arrays, another ECM tool.
Similar idea, but the beam directions are fixed by the physical design independent of the frequency used. Good for certain self-protection scenarios where you might face many threats across different frequencies simultaneously.
Okay, so we have the basic transmitters and receivers too, the building blocks. It's a lot of interacting hardware.
It really is. And the source makes a good point distinguishing ESM from SIGINT and signals intelligence.
Right, ESM is tactical, real-time for the battlefield.
Yes, SIGINT is broader, more strategic. It involves collecting signals over time, doing deeper analysis, often non-real-time, for bigger picture intelligence. ELINT, electronic intelligence on things like radar and communications intelligence, are parts of SIGINT.
ESM for the now, SIGINT for the long game. What about COMET receivers? How are they different from radar intercept receivers?
They're tailored for communication signals. Comms often use specific channels, maybe higher power, wider beams, and modulated continuous waves, not pulses like radar. Plus, you have encryption, frequency hopping.
Things designed to make interception harder.
Exactly. So COMET receivers need to be adaptable, able to handle these complex, dynamic signals. It's like trying to follow coded whispers in a noisy, crowded room where people keep switching languages.
A tough challenge. The source stresses studying the operational environment for designing this gear. Seems vital.
Crucial. You need to know what the normal signal background looks like, all the friendly, neutral, and enemy signals to design equipment that can pick out the specific threats you care about. Filter the signal from the noise.
And effective ECM needs both strategic and tactical info.
Absolutely. Strategic info is knowing the enemy's systems, their specs, how they usually operate. That helps you design your countermeasures. Tactical info is what they're doing right now, which radar is on, what frequency, how are they reacting. That tells you which countermeasure to use immediately.
Know the enemy's playbook, but also watch what they're doing on the field right now.
Okay, so ESM objectives. Detection, frequency estimation, direction finding. The core tasks.
Those are the big three. Detect a signal's presence, figure out its frequency, find where it's coming from, put them together, and you get a good picture of the threat.
And there are lots of receiver types mentioned: crystal video, superhet, microstan, each with pros and cons.
Exactly. No single perfect receiver. Crystal video is simple but limited. Superhead is selective but maybe slower. Others are fast but maybe less sensitive. So you mix and match.
Often, yes. A hybrid approach, combining different receiver types, gives you the best overall capability to handle a complex signal environment, like having a toolkit with different wrenches.
Right. And finally, for EW, countermeasures against ESM. How do you avoid being detected electronically?
MCON is key. Limit your own emissions. Turn things off or use them only when absolutely necessary. Design sensors to transmit only briefly. And use passive weapons like anti-radiation missiles or heat seekers, which don't give off electronic warnings themselves.
It's that constant cat and mouse game.
Always evolving.
Okay, let's switch gears then. From manipulating signals to manipulating shapes and materials. Stealth aircraft design, or low observability.
The other side of the coin, making the aircraft itself inherently harder to detect by any means.
Our source lists 4 key ways: visual camouflage, low noise, low infrared emissions, and the big one, small radar cross-section, RCS.
And while stealth can cover all that, it mostly means reducing RCS and maybe IR signatures too.
So focusing on radar, how do you shrink that RCS? The source mentions passive and active wave cancellation, RAM, and shaping.
Right. Passive cancellation is tricky. Active cancellation, where you transmit an out-of-phase signal, is theoretically possible, but extremely difficult in practice. RAM radar absorbent materials is important, but the most fundamental aspect, dictating the whole look of a stealth aircraft, is shaping, reflecting radar energy away from the source.
Let's touch on visual camouflage first, though. The original stealth, still relevant.
Surprisingly, yes. If you know the background, ground, sky, you can choose colors and patterns to blend in. Think darker tops to blend with the ground from above, lighter undersides for the sky from below. Standard practice, really.
Isn't that weird finding about pink for low-flying planes?
Yeah, counterintuitive. Apparently, pale, desaturated colors can diffuse light and blend well at distance in certain conditions, like haze or twilight. But the general rule is light gray for low flyers, darker for high flyers. Black is actually bad for low flight visibility, hence its use on trainers.
Makes them easier to see for safety. And those dark blobs on top surfaces.
To break up the shape and counteract the sun, making flat tops look brighter. Visual tricks.
Okay. What about low noise? Avoiding being heard.
Our source mentions those ultra-quiet spy planes from the Vietnam era, like the Lockheed Y-03. They went to incredible lengths modifying engines using special propellers.
Making them virtually silent from the ground.
Exactly, for low-altitude, covert recon. Interestingly, those quiet planes found later uses with NASA, FBI, wildlife agencies. Stealth tech finding other niches.
Fascinating. But back to radar RCS reduction through shaping. How does that work?
Well, radar sees by detecting reflected energy, like light bouncing off an object.
A big, flat, shiny surface facing you reflects a lot back, like a mirror.
Right, and a sphere always reflects some energy back, no matter the angle. Stealth shaping avoids both. It uses flat panels, but angled so they reflect radar energy away off to the side, not back to the radar receiver.
Like angling mirrors so the reflection goes somewhere else. The flying wing designs, like the B-2, are prime examples.
Perfect examples. They reflect energy in just a few narrow directions. The radar has to be in exactly the right spot to get a strong return. Reduces the odds of detection dramatically.
And a huge part of this is avoiding right angles.
Absolutely critical. 90-degree corners, like where a wing meets the fuselage, or in rectangular intakes or vertical tails, they act like perfect retroreflectors. They bounce radar straight back to the source.
Like the corner reflectors you see on bicycles or road signs.
Exactly the same principle. So stealth designs use angled canted tail fins, like the F-22, or eliminate vertical tails entirely like the B-2. Intakes become diagonal or have curved edges.
And serpentine intakes, those S-shaped ducts.
That's about hiding the engine face. The front fan blades of a jet engine are highly reflective metal. Serpentine ducts create an S-bend, so radar waves going into the intake bounce off the absorbent walls of the duct and get weakened before they can hit the engine face and bounce straight back out.
A radar maze inside the intake. Clever. Used on the F-22, Rafale.
And others, yeah. It's a key technique.
Okay, beyond shaping, there's RAM, radar absorbent materials, the stuff that soaks up radar.
Exactly. Instead of reflecting, it absorbs the radar energy, converting it mostly into tiny amounts of heat. Research goes way back, but the F-117 was the first big success using it extensively.
How does it work? Is it like paint?
It can be paint-like coatings or structural materials. The basic idea is that certain materials resonate at radar frequencies and dissipate the energy. There are different types mentioned.
Salisbury screens, Dallenbach layers.
Right. Salisbury screens are simpler, tuned for specific frequencies. Dallenbach layers are thicker, aiming for broader absorption. Gradient RAM uses layers with varying properties to absorb across a really wide frequency range. It's complex material science.
Always trying to counter more types of radar.
Sure.
The source mentions iridescence as a side effect sometimes.
Yeah, with thin RAM layers, interference effects between reflections from the top and bottom surfaces can occur, sometimes causing visual effects like an oil slick colors changing with viewing angle, a physics quirk.
Interesting. Now, the physics of detection range the inverse square and inverse fourth power laws. This sounds important.
It's fundamental to understanding why stealth works. The inverse square law just says energy spreads out, so intensity drops with the square of the distance, light, radio waves, sound.
But for radar, it's worse. The inverse fourth power.
Because the signal has to travel to the target, distance squared loss, and the echo has to travel back, another distance squared loss. So the received power drops off with the fourth power of range.
Meaning, if you double the distance.
The echo strength drops to 1/16.
Huh?
124. Conversely, halve the distance, and the signal gets 16 times stronger. It falls off really fast.
Wow, so even a small reduction in RCS has a big impact on detection range.
A huge impact. That's the key takeaway.
Which brings us to the point. Stealth is not invisibility.
Absolutely not. It just reduces the reflection intensity, meaning the radar has to be much, much closer to get a strong enough echo for detection.
That 100-mile detection range for a normal plane might shrink to just a few miles for a stealthy one.
Right. And the source gives that startling figure. To cut detection range by 10 times, you often need to reduce the RCS by 10,000 times.
That's incredible. Shows how effective RCS reduction has to be.
It really does. It's about delaying detection, reducing warning time, and making targeting much harder for the enemy, shifting the odds.
Well, this has been really illuminating. We've covered a lot, from the electronic games of EW
Jamming, deception, listening.
to the physical science of shaping and materials and stealth design.
Trying to make aircraft slip through the net electronically and physically.
We saw the early impact with the Bekaa Valley example and how complex both EW and stealth have become.
And it's clear this evolution isn't stopping. It's a constant push-pull.
That ongoing cat-and-mouse game between detection and evasion. New radars drive better stealth drives new detection methods.
Exactly. Which leads to a final thought for you, the listener. As these technologies, EW and stealth, get more integrated and spread across air, land, sea, even space, what might be the next big leap? What future innovation could fundamentally change this balance between being seen and being unseen in conflict?
Something to ponder. It's a question that will definitely keep engineers and strategists busy for a long time to come.